Okay, get started this morning. And that was Fleetwood Mac, and what was the choice there, Jonathan?
That was Never Going Back Again.
Never Going Back Again. Okay, we got the microphone on and sort of dragging a little bit in terms of getting things done with the grading and such, but I've returned a quiz up here. We're in the side table from last Friday. And that's your first grade on the quizzes, so you need to take a look at that. Food. No. Generally speaking, we won't do that in here. Okay, finish it up today. But now, one of the comments from homework from yesterday. How did things go? There's one question that was brought up about how to, I think, answer a problem. We'll look at that here in a moment. So I need to do that. And just a comment, we will be working on formulas today. So just a reminder, that's where we're headed. So with all that said, let's try to answer the question. Now, it had to do with which problem? Marisol? 1-4? Okay, I'm going to limit it for the moment to the 1-5. Let's deal with that first. Michael.
No problem. It's 9 squared minus 63 divided by, or over 29 minus 3, then parentheses 1 plus 2, parentheses 2 exponent.
Okay, let me write that on the board here in a moment. Okay, but let's deal with one at a time because that's all I'm going to be able to do. And just a comment regarding lunches and such, this is a no-eat zone. Okay, so we'll let it go with that today, but in the future, no. Let's try, Michael, putting the problem as you have it. Would you give me the numbers again, please?
9 squared minus 63.
9 squared minus 63.
There's that line under it.
Okay, a line underneath this.
29 minus 3.
29 minus 3.
Parentheses 1 plus 2.
Okay.
Parentheses 2 exponents per square.
That's your problem.
Yeah.
Agreed? Thank you, Jessica. Now, in terms of what we have here, what Michael just did is really something that's an important thing for each of you to do. And that is be able to verbalize how a problem should be written. It's really not as easy as it sounds with some of these expressions. So when you think in terms of in the numerator, I will have the expression 9 squared minus 63. The denominator, and that specifies that I'll have it underneath. So in the denominator, I will have the 29 minus the product of 3 times the quantity, 1 plus 2, quantity to the second power. A variety of ways of saying it. But trying to articulate is really important. And I get involved with this a lot over the phone. Somebody calls in and says, here's the problem I have. And then they have to try to specify to me what's there. And then I've got to be able to feed back what it should be. This is in essence a division. Because a fraction is a division. So this would be possible of putting parentheses around this whole thing, a divide symbol, and then braces around that whole part. So I simplify the numerator, then I simplify the denominator. So in my in-between steps, I would take the exponent first, which is 81 minus 63. In the denominator, I should do the exponent first. So if I'm going to do this sequentially, I would have 29 minus 3, then I would have parentheses 3 here to the second, so I do have to do the parentheses first. Then the next step, and I would be inclined to go up here in the next step and actually write at this point that I have an 18. Okay? Otherwise, the 81 minus the 63 at 18. So I'd have an 18 there. Now I'm going to leave this as 29 minus a 3 times a 9. Now, there are a variety of ways of writing this because I wasn't obligated to simplify the numerator. But this then is going to be 18. Then I have a 29 minus a 27, which would be a 2. And because of space, I'm shortcutting that, and I get to 9.
I see where my error was.
Okay, you got it?
Yeah, my error was, I got some random number here, I don't know.
But at the time, it made sense.
Yeah.
Okay.
I did it.
But as long as it makes sense now as we go through it. Okay. Robert.
Okay. I know that the order of operations multiplication or division, right?
Not necessarily. The question was, in order of operations, a multiplication comes before division. Not as such. It's whichever comes first as you scan from left to right.
Okay, and this problem, multiplication came first, but still, they said you had to divide first.
Okay. I said I would answer Shamra's question next, but let me take what you got there. Can you read me the problem, Robert?
Okay, 3 times the square root of 16
Okay.
minus 24 divided by 3
Divided by 3
times 2
times 2
plus 19.
plus 19. Okay, what takes priority here? The square root, agreed? And that is an understood multiplication in front. So this, I guess since we used a times there, I'm free to use the x there. So I have 3x4. Kim? Pardon? Ah, good question. How do I know that that 3 in front is not an index? 2 answers to that. 1, the text has not talked about cube root. Second point, juxtaposition. How close things are to each other. I remember my mom and dad taking drives to the Bay Area when the Altamont Pass was a 2-lane road with a passing lane in the middle going uphill. So we got behind people, and you stayed behind them for a long time. So they'd start discussing the people in front of us in the car ahead to pass the time of day. And if it was, in those days, a bench seat, so you didn't have the bucket seats. And so 2 people were in front of you, and they were this close together. They figured they weren't married yet. Certainly didn't have kids. And if they were this far apart, then they obviously were either married and had kids, or were having an argument, but there was something they made a choice on by how close they were together. That's juxtaposition. So in that sense, the 3 close to this square root says you're multiplying. And we learn to understand that as we work with mathematics. It's not something that's explicitly stated. So that's why that was a multiplication. Next, since this is the division I see first, I would say 24 divided by 3, which is 8, times the 2 plus the 19. I'd come back and probably say I have a 12 here minus a 16 plus a 19. And I'm not real happy with what just happened there. Because if you were to go ahead now and do additions and subtractions in order given, then we find ourselves before we should be, if that makes sense. Because it's in 2-1 that we're supposed to see what? Negative numbers, negative integers. And if you have a 12 minus a 16, that's going to give you a negative 4. So what I would be inclined to do is say 19 and 12 is 31, minus the 16 is 15, but that was a poorly given problem if I haven't made some blatant error in what I've done here. Balmaro.
But it's doing the same thing if you put 12 minus 16 and then plus 19.
Well, I can, but 12 minus 16 is a negative 4.
Yeah.
And the negative 4 plus 19 is 15. I'm just saying the intent here is to keep you in whole numbers. By making this subtraction your next step, it's not a whole number. That was a badly chosen problem. Did this come out of the computer? Okay, so it was a problem that shouldn't have been created. I don't see a way of getting out of this and avoiding that negative. Michael?
I just assumed that you put the 16 on the top and the 12 underneath and subtract.
Yeah, but you can. But if you do that, even if you say this, you still end up with an...
No, the 16 on top.
Not true. I mean, that's the way of getting around it, but this is a subtraction. It's not reversible. So the point is, I mean, if you're going to take 12 and subtract 16, it's not the same as 16 minus 12. It was a poorly randomized problem, and I apologize.
I got it right now.
What about multiplying the 3 times 2 first, and then dividing it?
No, I have, well, the question that's being asked, what if I did the 3 times 2 first and then divided? What would I have to do in the problem to indicate that to the reader? The parentheses around the 3 and the 2. Then it would be viable. But the way Robert gave it to me, there was no parentheses. Is that correct? So it's one of those cases, they were just writing up what we think of as randomly selected numbers for problems, and somebody didn't check to see if you happen to get in the process a negative number in the middle. So a glitch, but one I hope that's acceptable for the moment. This says the temperature's 12, it drops 16 degrees, you're at minus 4. That makes sense? Shammer.
Mine was the same like that.
Okay, same thing. Another one like that. Wow. So we had a couple of them where you ended up with a negative value in the middle. Okay, and that is in section 1.5. So, you too, Nancy? Good. Okay. Larita, you have the connection that you can share with them about where they might get a free cup of coffee. And in terms of this process, I think this is one that should be reported to the extent you should be getting whole numbers and not intermediate values that are negative, and most certainly not a negative number at the end. So this was a case where they just weren't being quite careful enough in their selection of numbers. And when you do random selection of values, you forget that in between, otherwise they're saying at the end you get a positive, that's good enough. But nobody had the forethought to go back and check the intermediate step. And when somebody got a negative number at the end, that should have been a red flag saying we're in trouble.
They have it in their when you log on to the website for Compass, on the side it says 24-hour technical support. You would contact that number and call them without the first 5 people.
Okay, so on the Course Compass page, left side, they have a 24-hour hotline kind of thing. And if you're one of the first five, so give it a try. And again, this would be a case where creating problems for any book, you have to be really cautious when you're restricting yourself to closure. I got to come back to that. Remember what the closure was? What did it say? If you multiply 2 numbers, you should get what? The same kind of number you started with. So if you're in the reals, you should get a real. So if we start with the whole numbers, closure says I should get a whole number at the end. Right? Whether I'm adding or multiplying. So in the process we're going through here, because we're dealing with multiplications and divisions, there's no problem here with using closure for whole numbers. With the products and the divisions, it's my additions and subtractions that I don't have the closure. I'm getting some values that end up negative, which are not whole numbers. So this is not a closed set relative to the operations I'm using. So you don't get too critical of this. Writing problems for this set, you have to be really cautious. And when you're trying to generate them at random to have 1,000 or more problems available for everybody doing their own version, it's easy to slip one in like this. Michael.
Even if you had a negative 4 minus plus a positive 19, would it be 15?
Yes, the answer doesn't change. The point is, in the middle, I get what? Doing the order of operations. 12 minus 16, I generate a non-whole number. A whole number has to be a positive counting number or a 0. So you generated something we aren't supposed to be into yet. Section 2.1 is where I finally hit the negative integers. So it was an unfortunate bridge that most of you seem to have handled with aplomb. You didn't get real upset. I'm pleased about that. You got around it, but you understand that it was not the way it should have gone. Any other question? Does that cover the questions? Now, anything else in 1.5? Okay, now, Marisol, back to 1.4.
Okay, so the number,
The number.
the question says, choose the numbers that are divisible by 5.
Okay, so the question, and I'm having to repeat because I'm assuming Jonathan can't pick that up on the microphone. The question has to do with numbers divisible by 5.
Yeah.
So should I just write some numbers down just for the heck of it?
Yes. Yeah.
Okay, so randomly selecting numbers divisible by 5. Okay, James, give me a number divisible by 5, but keep it modest, 2 digits. 30, okay? Michael, another number divisible by 5. 5. Okay? Emily,
270.
2 digits,
Oh, 2, I don't know.
or 1 digit, but 2 or
65.
65, okay? Let's go one more number divisible by 5. Isaac.
35.
35. Okay, now what am I supposed to do?
Add the numbers.
Yeah, you have to have numbers that are not divisible by 5 too. Because it says choose the numbers
have to be
that
mixed
are
up.
divisible by
Yeah.
5.
Okay, so I have another, so I'm going to have something like 77, 30, 16, 5, 28, 65, 17, 35. Okay, so I've got a set of numbers. Some are divisible by 5. Now what?
Now you pick out choose the ones that are divisible by 5. So I would say
Which are the ones up here?
30, 5, 65, and 35. Then I would put them into the computer like that, but it wouldn't take it. It wanted it in a certain
It wanted it sorted from small to large?
No.
You got to put a comma.
No, it wouldn't even work from small to large.
Okay, James.
I showed Gloria the problem yesterday.
Hold on, James. And you had to sort them. Did you have to put commas between?
Yes.
Commas between from smallest to largest. So you were expected to go 5, 30, 35, 65, and then the computer accepted it for you. But it liked you. Now, somebody else tried it and they didn't like you. Larita.
Marisol has the exact numbers that she entered, and she tried to have me help her, and I did it from small to...
Some weird order that wasn't any of the above. Well, she left it at home.
Oh,
That's the problem. Okay, before I get to Dion, in this process, if you again have what you think is right and somebody else is working with you and you're pretty darn well convinced, get on the phone and make that call. It's a free call. And just indicate there's no rhyme or reason. And it could be that simply that somebody was writing the numbers in a different order. I would expect either small to large or large to small. But if it was some other random order, and that's what order you had to be in, then you're fighting the computer. So be cautious. Don't overly fight the computer. If you had trouble and it's not making sense, I think I would go through and do what? Well, first, I tried to get a new problem. And then see if the next problem worked as well. If you're still getting messed up, make sure that you are getting the correct numbers. And then see if doing large to small, in this case, works. I don't want you fighting the computer too much. Okay, then come back to class and talk about it, and then if it's still a problem, we can either call it in or so on. Dion.
I think the problems are set up to see if you really know what is divisible, like what numbers are divisible by, because I found out, like, I had to put in a certain order too, from smallest to largest, and on, like, similar problems, I just put random and it would take it. You know what I mean? Like.
Okay, so there was no particular... Did you,
Yeah, like-
whoever did it, and it was in a different order, did you try the commas and that still didn't do it? Now, is it comma and a space?
No, just comma.
Just commas, but no spaces. Okay, I don't have a quick answer, and I don't want to waste too much time talking about it. The key is, could you find numbers divisible appropriately? Our problem is entering it occasionally, and if there is a glitch, we need to report it. Michael, last comment.
Well, I mean, what worked for me was just as you looked at the numbers, put in the number that was divisible, and that worked.
Just in the order given.
Yeah.
Okay, it should be unforgiving, and I would assume at certain points, different people are working in different problems. So what maybe works for you, somebody else wanted to be in a sorted order, that should be fairly consistent or shouldn't matter. The fact that it seems to be a problem, I would still be inclined to call that in and say, here briefly is our problem, and see what happens. Draw straws for who gets to call it in and get the free coffee. Any other questions now? Have we got everything unresolved? Dion.
Yeah, I do. How you did this problem right
Okay, I'm going to slide over, Jonathan, over here now. As I come back to this problem,
I think I heard you mention, I'm not sure, I just want to be sure. Like, the way I was doing the problem, like I know how it says, please excuse my dear Aunt Sally or whatever, but I
Yes.
found it good just to do, I focused on the top, and then I worked on the bottom, even though I was supposed to start with the parentheses, and then...
Okay, I agree.
I just started with the top.
yeah, when you have a fraction, and the comment being, the little ditty we sing, or say, please remember my dear Aunt Sally, kind of, or please excuse my dear Aunt Sally, or please remember my dear Aunt Sally, to get R in there for root. But in this process, it sometimes makes sense. Take care of the top, take care of the bottom, and then apply what you're doing. I agree. I agree. Totally agree with you. Anything else there? Then we can move on. Good. I've got space over here still. Question, Nancy?
Yeah, so division comes before multiplication?
No. The question being asked is division come before multiplication. Jonathan, we slide over again. In terms of what I have here, I did the division first because it came first. If I had had the 2 here and then the 3 over there multiplied by 2 divided by 3, I would have multiplied first. Whatever comes first as you go from left to right.
What about subtraction and addition?
Subtraction and addition, whichever comes first as you go from left to right. Whatever you bump into first, do first. But you do multiplication and division first, and then rescan additions, subtractions, in order given. Agreed? Now can I go on? Thank you. Formulas. Volume of a box. What is the formula? Volume of a box. Not a square, of a box. Box. 3-dimensional. Okay, volume is LWH. Length times width times height. And I know to multiply because they are sitting close together with no space behind them. They like each other. Okay, LWH. And so if I have a box, you remember how to draw a box?
Yep.
I hope you do. I'll sketch one. Say a cube, I said a box. Remember I have 2 rectangles? And then what do? Join the corners. And I'm just sketching it without a straight edge. And then I make dashed lines for the things that you should not be able to see if you were looking at it in a particular format, and that's my box. Technically, a rectangular parallelepiped. I wanted to say that because today we introduced parallels and parallelograms. I'll say that later. We got a box. Let's say it's a room, and it is 8 feet ceilings, and this is going to be 12 feet this way and 9 feet this way. So I've got a room. What is the volume of that room? If I'm in your way, look at the monitor. What's the volume of the room? Well, I'm going to substitute into here. Remember, formula, substitution, answer, and draw a picture when appropriate. We got it? So the length is what? 12 feet. I'm going to write the feet as an abbreviation instead of the single little hash mark. Times, I will use a multiplication symbol here just to keep that straight. The width is 9 feet. And the width times the, see, I had length, width, and height, 8 feet. So a reminder that the units are very important here. We're going to have what? Cubic feet or feet to the third. Recall that. Volume is going to be cubic somethings. So in this case, there's not much nice about this. We have 72 times 12. So if I put my 72 here, I put my 12 here, I've got 144, I have a 72, and so I have a 4, a 6, and an 8, correct? So I have 864 cubic feet or feet to the third, your choice. There's nothing particularly new about that, correct? You've been there before. But I'm going to remind you of something. So at this point, I'm going to write up here something else we did. Do you remember this formula? Base times peanut butter Reese's, yes. But this is courtesy of, was that you, Richie, that did this? Okay. But this was base rate and percentage, correct? Then I said if you wanted the rate by itself, what did you do? You could use the triangle. What else could you do? Divide by what? The rate by itself. R by itself.
Divided by the whole.
Okay, part divided by the whole or the base. So I made a comment last semester that I could think of dividing both sides of this formula by the same letter. And get the following. R is equal to P over B. Now the question, why would I do this? So I only had to memorize one formula. Because out of P equals B times R, I can get R equals P over B, and I don't have to memorize another formula. I could also divide both sides by the letter R and get that P over R is equal to the base. And we used that problem. We had 3 different problems. That's a process we used. Now, this was a formula. I need to slide over just there. That's a formula. Can you solve that formula for H? The part I'm pointing to. No, it's no. This V equals LWH isn't P equals BR, but what I did there I want to do here. Same idea. What could I do here to get H by itself? Divide by what? The length and the width. LW. Watch. I'll get out of the way here in a moment. The LWs cancel. And I have H by itself is V over LW. It got very quiet. I just asked you to take a big jump. Now I'm doing the same thing as Emily's comment was. How does that have anything to do with this? What we did there, I'm going to do here because I didn't want LW in the right side, so I divided the right side by LW to get H by itself. Yeah, I canceled the L and the L and the W and W, and I was left with H. Precisely. Okay, Jonathan, you need to go camera 1 here, so I have camera 2 free over there. And as we do that, I'm going to look at this in a slightly different way. There's 2 versions of this. And by the way, this is part of algebra. Okay, we have a whole set of problems in algebra where there are a bunch of formulas, and you plug in values just like I did here, and you get the volume. Then we have a whole bunch of other problems saying, okay, now I want you to solve for the letter H with that formula. In between, I'm going to leave that there, and I'm going to walk off camera and go to space. So as I go over there, let me come back to this problem. Now notice I'm not putting x's between. The closeness tells me multiply. But I'm going to change the problem slightly. This is the in-between, between the easy and the hard. I'll tell you the volume is 24 feet cubed. I will tell you that the length is 3 feet. I will tell you the width is 6, no I won't, is 2 feet. And I want you to tell me H. Now that's the in-between problem. You'll have a whole set of problems like that. So you have these numbers, so you're going to substitute these numbers for what's up here. Again, follow what I'm doing. I'm going to take each of these 3 numbers and substitute what I have up here, and let's look at what we get. So I have 24 feet cubed is equal to 3 feet times 2 feet times h that I don't know. Let's forget about the feet for a moment and just write this as 24 equals 3 times 2 times h. Now you follow, I hope, that that's 24 is equal to 6h. And we had a series of problems where you knew the shortcut, the related equation is to do what? Say h is equal to 24 divided by 6, and so you know your answer is going to be 4. Hence, 4 feet. Do we agree? The shortcut is to come back to here, slide over now, and say, if I have V equals LWH, and I want H by itself, I divide both sides by LW and get V over LW. There's my new formula. Now I can go back to the new formula and say that if H is equal to V, which is 24, over L times W, which is 3 times 2, I get 24 over 6, which is 4. I have to put the units in. Michael. This is solving a formula for one of the letters in the formula. Now, what I did here, by going from here to there, you've got to watch where the here's and there's are, going from the general formula to one of the letters is not the easy part. That is challenging you. There are steps we take. Some of them go up higher than others. So sometimes it's a little baby step and sometimes it's a cliff. I just ask you to go up the cliff. But it's a good venture. Okay. Well, time to draw a picture. Now, we had things like this, just to remind you. Remember problems like this? Didn't just ask if you liked them. I just said if you remember them. And I ask you to find areas. Okay? So if I looked at this and this was, okay, just a moment. Say this was 12 and this was 5 and this is 13 and this is, say, 14 feet, 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 feet. Now why does this That looks like a double hash mark. Why is that a good choice on my triangle? Somebody argue. Remember some guy who was Greek. Okay, Pythagoras, and it's? You're close. A squared plus B squared equals C squared. Very good. A squared plus B squared equals C squared. That was A, B, and C. C's the diagonal. So I look at 5 squared. I look at 12 squared. I look at 13 squared. 25 plus 144. Is that 169? It is. And I have checked my problem. So that was a good diagram, even if you didn't like it. And what did you do to find the area? You treated it as 3 different shapes. A triangle, a rectangle, and a half circle. Agreed? You've done those. I don't need to do that again, just to be doing it. Then we had another problem. Pardon my circle. Half circles. Okay, if this, well, that's it. Hold it. Now that's interesting. Sometimes when I look at things here, I don't see what I can see looking at the screen. Can you see half of a cylinder on the screen? But looking on the board, it's hard to see. But looking on the television screen, it's easy to see half a cylinder.
It's like half a basketball court.
Okay, I'll buy that. However, that wasn't where I wanted to go. At any rate, let's say that this is 12 feet here, and this is 6 feet here. I want to know the area inside that shape, and you have 10 seconds. Well, inside what's in solid lines. You went past your time frame.
72.
Very good. 72 square feet. Defend it. Michael?
Well, because you got the circle going in, you got the circle going out, they cancel each other out, and you just multiply the 2.
Very nicely stated. This cut off, fit it in here, and you have a rectangle. So if you cut out this half circle and glued it to here, it's the same area you would have had if you just had the rectangle. Now, if I take that off, not so easy, right? Because now you find the 72 square feet and subtract off the area inside that half circle. And we did that kind of problem, where I had a triangle cut out. If you refer to your notes in Math 10, you would have found something like that. Okay, that's the kind of thing that you're going to have for problems in homework. So I'm going to go leave this half a cylinder that I see there, coming back to the book. And let's see the kind of diagrams that are drawn here playing the same game. Now, the first part, as I come back to the book, just a reminder, I'm on page 63. As we go to the document cam, Jonathan. We have a right angle is an angle that measures 90 degrees. We've been doing that all semester. That's at the heart of Pythagoras, a right triangle. Now, we have a shape here that looks like a rectangle that wasn't braced for the wall of a house and it's starting to collapse. It becomes a parallelogram. Parallelogram. And as I come up to a little bit higher, I'll just slide up. Here is where it's defined for you. A four-sided figure with two pairs of parallel lines. And we have a parallel line defined up here. Okay, straight lines line in the same plane that do not intersect. Okay, coming off there for a moment. We've introduced an idea that is not probably familiar to you of a plane. and it's not the plane you fly in. A plane is like a flat surface, a level surface, a flat level surface. So we think of that as a plane. Then, parallel lines are two lines drawn in that plane that do not meet no matter how far you extend them. That's what makes them parallel. Now there's a classic problem out of geometry done by Euclid. Okay? And Euclid was another one of those Greek mathematicians, and he wrote a number of books on geometry, which became the textbooks for mathematics for centuries. The 13 books of Euclid. And in that, he had a statement that if you have a line, and this is not much of a representation of a line, but let's try to get it so it looks a little bit like a line, and you take a point not on the line. So I have a point up here, just some point in space. Then through that point that I'm pointing to with my index finger, there is only one line parallel to this line. That may seem obvious to you, okay, but it was very critical. You have a line, and through a point not on the line, there's only one parallel. So if I look at a piece of paper, and I think of my pencil here being like a line. Now, a line shouldn't have thickness to it, but this one does. And through a point, not on the line, big point. Points aren't that big. So shrink that down like an Alice in Wonderland so it just becomes a point. Through that point, not on the line, there's only one line parallel to the given line. And that was called an axiom or a postulate of Euclid. If you have not a flat surface and you think like a sphere, okay, and the idea that things don't intersect, okay, then you could have more than one, was the idea, and that became non-Euclidean geometry. So this whole idea of parallels is very important. And if I have two parallel lines, then the distance between them is equally spaced as we go back to the diagram. The space between those two is always the same, parallel lines. Now, if I have these two parallel lines, and then I take another two parallel lines, that creates a parallelogram. Got it? And I can shift it in a variety of ways, but by pairs, they are parallel. Now the question is, how do you find the area inside a parallelogram? Before I go to that, Michael, as we come off here.
The reason they said there's only one
Parallel?
is that because if there was a third one, they wouldn't be able to connect?
Well, if you had a third one, it would be on top of the other. So you think of one line having to be on top of the other. Play with that a little bit. I don't want to take too much time in class. It's not something you can prove. It was a statement that you said, I believe these to be true. Remember we have 11 properties of the real number system? Well, there were the 5 postulates of Euclid for plane geometry, that flat geometry. So there were 5 statements, I believe this to be true. And so, given a line, point not on the line, there's only one line drawn parallel to the given line. That was one of the 5 things. And off that, you could prove everything else about geometry. Given the 11 properties of the real number system, I can prove everything about numbers. And sometimes you decide you have fewer statements you want to believe. So there is a smaller set of axioms or statements we take to be true that will generate the real number system. The 11 we use work well for algebra. With that said, remember what I did on the sideboard, Jonathan? If you'll go to the sideboard with my half circles. Remember we said we could cut the one off on the right, paste it where the one was cut out on the left, and it'd be a rectangle. Okay, play the same game with this diagram. Here's your parallelogram. Cut out the right triangle, paste it on the right side, and you have a rectangle. So the formula for the area of a parallelogram, as we come off there, is exactly your formula for the area of a rectangle. Base times height. No, just base times height. Or length times width. Now the problem is, let's come back to this diagram. This height we usually think of as h, where you normally would think of this rectangle length and width. So when you think of, off there. When we think of a triangle, you think of 1/2 the base times the height. Here we have a parallelogram. We talk about base and height, but it's no longer a triangle involved. So you take the base, which is this distance from here to here, and the height of that triangle, if you will, dropping a line from this point down here. We call this a perpendicular line because it makes a 90-degree angle. But usually, if you're given a parallelogram, they'll just give you the base and the height.
Is there an abbreviation
For a parallelogram? No. Yeah, it is a long word, I realize. Now, to say that you have a rectangular parallelepiped, rectangular and parallel. You know what parallel means, you know what rectangular means. So you're getting closer to what a rectangular parallelepiped is, which is a box. No, you can spell rectangle, and now you can spell parallel. Okay, so you're getting close. There's a nice little diagram given on page 64 that you'll appreciate at this point. I'm being very proactive here. I know you'll appreciate this. This is on page 64 if I can get the camera to hold its position. I can't, so I'll just hold off here. Now, if I have a little ice cube, okay, 1 cubic centimeter, that is a cc, cubic centimeter, 1 centimeter on each side, and then you have a cubic inch. Then we have a problem, which is a box with meters down here at the very bottom, and they're trying to show you how you can stack little boxes in the big box. Coming off there. Remember I gave you this problem? You had an ice block of ice. It was 12 inches by 12 inches by 12 inches. And then if we cut it along the inch markers each direction in 3 different cuts, you could get 1,728 little ice cubes, 1 inch on each side. Same idea. To visualize. So one of the things that's done in this presentation is ask, how do you solve problems? Problem solving. It's not as easy as we think. Because you see a word problem, what do? And so this author tries to give you some approaches to problem solving. A lot of material has been written on problem solving. George Polya, who was a mathematician at Stanford University, who died at the nice prime age of 97. 97 is your last prime under 100. So I thought he did it in style. At 97, he died, and that's not too many years back that he did, but he was a mathematician who wrote about problem solving. He wrote a classic paperback called How to Solve It. But I had the great opportunity when I was attending the Santa Clara University, and Stanford was just across the way. Polya would come as a friend of the university and run seminars and discussion sessions, so we had an opportunity to work with him. And that was when I was doing my master's program. And he made a statement that I thought had a lot of meaning. Don't try to solve a problem until you understand it. That's a fairly common sense kind of statement that applies to life. Don't try to solve a problem until you understand it. How do you understand a problem? Talk about it. First thing, if you can't say what the problem is saying without reading it, you shouldn't start trying to solve it. Any word problem. Be able to say it out loud without reading it. And then be able to draw a picture related to it. At that point, you should consider solving it. So then the question is, what kind of strategy? Often, a formula is what you'll have to use. Okay? Then, once you have your formula, make your substitutions, get your solution, and check your answer. That is the approach that Polya essentially recommended. And by the way, it's interesting to note that typically we expect you to be able to do that in 5 minutes in a test question, where you really should have what? An open-ended time. One of the most fascinating courses I took in my master's program was to give you a problem to solve by next week, following that strategy, and maybe 15, 20 hours in the problem, with no guarantee you'll find a solution. It was not the low-stress method. Okay, I'm going to go to page 66. Problem-solving outline. In blue, understand the problem. Meaning, read the question, draw a picture if you can, and talk about it. That's what I said. Number 2, get a strategy. Hunt for a formula. Something that you can do to get an equation. Step 3, solve the formula. Mean, substitute. Get your answer. Answer the question. Check your results. And then, is it reasonable? Okay. Now that last one, you have to be careful of. If I ask you to find how long it took to do something and your answer comes out negative, if I ask you how long it takes to do something and your answer comes out negative, not reasonable. Okay, so you have to be cautious. Yes, that gets into quantum physics, where things happen before they occurred. Think about that for a moment. The Strange Story of the Quantum by Banish Hoffman, a contemporary of Einstein's, a great book by Dover to read about. Here's a diagram close to what we were talking about. This is to find, and this is a case where you have a diagram on page 69. Okay, and it is related to a diagram up here. Now you could find the area for these two, the rectangle and the square, or you could do what? Draw these two lines in. And hint, in geometry, the lines you draw in sometimes are critical. Let's look why. If I increase this up to here and here, I have a big rectangle. Then just find the area of the little rectangle I'm cutting out, and you have your solution. We call those auxiliary lines, lines that you add to the diagram. Look at the diagram again. When I talked to you last semester about this diagram I have over here on the board, if I didn't include those two auxiliary lines, you might not see what? That you really had a rectangle. By drawing these two dashed lines called auxiliary lines, suddenly, maybe you can see cutting this out, sliding over here, I now have a rectangle. And a hard problem becomes an easy problem. Auxiliary lines are critical to the solution. Back to the diagram on the document cam. Now, the only objection I have is I would like to have seen these lines that were added become what? Auxiliary lines by dashing them or something like that. Okay, and enough for that. And you have a lot of diagrams here very similar to what we'd done before. And I think I have done everything now that was in section 1.6. I like this section because it reminds me of what we did in formulas. Not much new here. Probably the one thing I did that was new was solve a formula for a single variable. And I did it a little bit beyond what's done in the book because I wanted to push you a little bit further. I know you appreciate those efforts I make to try to enhance your existence and mess with your head. Okay, just a comment. This is where this started. I have just enough time to do this on page 62. And I'm going to do something beyond where the author is. 62. Notice this formula. We were there before. What's an alternative using the distributive property? Don't get this, you don't get to leave. Back to the problem on the screen. Rewrite it. I'm 62. Look at the screen. I'm pointing to it with the pencil. What can you do with the distributive property? Rewrite it as how? Nobody? P equals what? No. No. Distributive property.
L plus L.
No.
P equals 20.
Okay, coming off there for a moment. Don't let them leave. No lunch. Okay, I'll write what I'm wanting you to go for using the distributive property. Okay, I hope. You're darn close. You should have said plus. There you go. Okay, let's go for it. That's using the distributive property, and we call that factoring. That's neat. That's good. That was worth being here today. Okay, with that said, I'm out of time. So we have Fleetwood Mac. You know the